Low. Mm. Oh.
New type of renewable energy conversion that is being researched on for a while. 1 minute, what happened? Is my slides are my slides shared?
Your slides are shared and you were on full screen, but now you came out of full screen. And
Okay.
if you can go back to full screen, that would be nice.
Okay, I'll just start sharing again then. Okay. I think now I'm on full screen, right?
Yeah.
Okay. So hello everyone, I am Mohammad Nasim Afustaj. Today I'm going to share about ocean thermal energy conversion, and one of the leading researchers in this field is Makai. So I'm going to focus on that. So what is ocean thermal energy conversion? This is a fairly new renewable technology that harnesses the temperature difference between warm surface water and the cold deep ocean water to produce electricity. This system works on the principle of using this temperature gradient to drive a heat engine, typically with a Rankine cycle. I think one of other previous presenters has shown what is the Rankine cycle to generate power. And Makai Ocean Engineering is a forefront of OTEC research and development, driving innovation in this field. So how does OTC works? In the right hand side, you can see two types of depiction of the same thing. There are a few key components: some pipes, some working fluid, pump, a condenser, evaporator, turbine, and generator. So how does it work? At first, the OTC system uses warm surface water from the ocean. Typically, the temperature stays around 25 degrees Celsius or 77 degrees Fahrenheit in tropical regions. It uses the temperature to vaporize a working fluid with a low boiling point, which is usually ammonia or something like that. This vaporization process occurs in the heat exchanger. After that, the vaporized working fluid expands the driver and drives the turbine connected to the generator. This turbine spins and generates electricity. But after that, the vaporized working fluid needs to be condensed back, and this is done by the cold deep ocean water, which stays nearly around 5 degrees Celsius or 41 degrees Fahrenheit. After condensation, the vaporized working fluid cools down to liquid form, and then it is recirculated throughout the process. So for this, it is very evident that we need tropical regions to perform this type of energy conversion. And here is a heat map that shows the highest heat gradient available all over the ocean area we have. And the most potential locations we have are Hawaii, Caribbean islands, Southeast Asia, Indian Ocean islands, Pacific islands, coastal regions of Africa, and Central and South America. Here you can see this is where the Hawaii Makai plant stands, and it's a onshore energy conversion plant. So here are the details about Makai Ocean Engineering. So it is equivalent to 105 kilowatts of energy for power. The working fluid here is ammonia. It is a closed cycle. So the closed cycle means the working fluid does never leaves the cycle, or it's an onshore plant. Uh, it's the seawater, so it sources its seawater by its sister organization NELHA, and it was established during 2011, and it started its operation during 2015. And here's the location, which is Hawaii. So now let's look into onshore and offshore options of OTC. So there are few problems and few pros and cons for both. For example, if the plant location is offshore, it needs to have a lot of stuff around it, like ships and other other maintenance things needs to be shipped to them in the middle of the ocean. But when it is onshore, it's near land, so it's easier to access. The proximity of thermal gradient, obviously, in offshore, the depth of the ocean is higher, so the thermal gradient is going to be higher as well. So it's directly below. But for onshore, the surface of the depth of ocean is not great, so we need to take the lower temperature from deep ocean that is far away from the source. For power transmission to grid, for offshore, it's obviously challenging to transfer the power generated, but for onshore, it's easy to transfer to grid. And cost of building is obviously higher for offshores, and engineering risk of gathering resources is very low offshore, which is very high in onshore. So based on all this, commercially, onshore ocean energy conversion is not commercially viable, but it's viable offshore. So Makai is now researching on different aspects of ocean energy thermal conversion. Some of it is seawater air conditioning. So seawater air conditioning is a sub-product of this renewable energy technology that uses deep sea water. They have the recognized lead, and Makai is the recognized leader in SWAC. Other one is Ocean Energy Research Center. It is also located in Hawaii. And OERC is demonstrating and improving the technology to harness thermal energy of the ocean, which is a primary focus of OTEC system. Research at the center also supports other deep ocean water technologies, including SWAC and marine heat exchange for various applications. Grid connected to OTC, Makai's OERC facility includes a 105 kilowatt turbine generator that became the largest grid connected OTC plant in the world when it was added in August 2015. This plant provides valuable data for developing OTC power control and automation systems and improving future commercialization OTC plant designs and cost projection. Other small projects include Hawaii 1-meter pipe repair, which is a final design and construction oversight for repairing deep water 40-inch 1 by 1 millimeter HDPE pipe that uses to collect the cold deep ocean water. Other things include Host Park Deep Sea Water Pipeline, Indian OTC Pipeline, Nelha 40-degree cold water intake pipeline, and Nelha 18-inch cold water pipeline, OTC pipeline research, and long operating OTC pipeline, and mini OTC pipelines, and etc. One of the leading researches they're doing in thin foil heat exchangers. So thin foil heat exchangers, or TFHX, developed by Makai Ocean Engineering, represents a revolutionary advancement in heat exchanger technology. Here, what makes this stand out? First of all, it is ultra compact. This significantly more compact compared to the traditional heat exchanger, allowing for a smaller footprint for OTC system and other applications. So it is easier to plant. Lightweight construction. TFHX is designed to be lightweighted, reducing the structural requirement and overall weight of the system, which can be crucial for offshore installation. Corrosion resistance. So TFHX is made from corrosion resistance material, which is such as titanium, ensuring durability and longevity, even in harsh marine environment. Form fitting. These can be customized to fit a specific space, constraints, and applications, maximizing the efficiency and performance. Improved performance. This provides higher efficiency and performance compared to the conventional heat exchangers, resulting in better energy conversion and overall system energy efficiency. And reduce material cost with versatile applications. So it requires less materials, so obviously less cost, and it has versatile applications beyond OTAC, including SWAC, marine cooling system, shipboard cooling, and thermal storage, making it very versatile overall. For the future outlook, Makai Ocean Engineering for future includes several key aspects. First of all, OTC is still in its very early stage, so they're focusing on commercializing the OTC. So they're further reducing, their focus is on further reducing the cost, increasing efficiency, demonstrating the viability of OTC as a renewable energy source. The involving research, ongoing research development demonstration projects to improve OTC system design and components. Expansion of THFX technology. So they are focusing on refining and developing this TFHX technology and aiming to commercialize it for various applications beyond OTC. This includes those systems we talked about earlier. Collaboration and partnership. So they're likely to seek collaborations from partner with other companies, research institutions, government agencies, and accelerate development and deployment of these technologies. They may involve in joint research project, pilot demonstration, and commercial ventures, market penetration, and diversification of services. So they are also focusing on expanding the market presence and penetration for both domestic and international markets. And also they are trying to improve people's view on OTC to introduce this as a viable renewable technology source. Now, what are the advantages of OTC? First of all, this is a baseload power generation. So OTC doesn't depend on other types of technology that depends on wind or solar that works at a certain part that time of the day, but doesn't on the other time. OTC system totally depends on the thermal gradient of ocean, which stays fairly constant throughout the day. So it can provide continuous baseload power generation since the temperature difference between warm surface water and cold deep ocean water remains relatively constant throughout the day and night. It is renewable and sustainable. It doesn't use any type of fossil fuel or any other source resources. So it is renewable and it produces minimal greenhouse gas emission. Which high energy potential. So if vast amount of solar energy is absorbed by ocean, so if we can plant a lot of offshore OTC plants, it has a potential to generate high amount of solar energy converted to workable electrical energy. Continuous operation, which I have already covered. Co-product utilization. The OTC co-products include the SWAC, seawater air conditioning, and it is nutrient, and it also can supply fresh water through desalination and nutrient-rich cold water to aquaculture and chilled water for air conditioning. Climate resilience. OTC can contribute to climate resilience by diversifying the energy mix and reducing dependence on fossil fuel, and potential for island nations. For island nations that is located in deep ocean, it is more possible to, it has more potential for them to produce energy with a lower cost. But what are the challenges in OTC? I have already mostly talked about them, so here are them in also. First of all, economic viability. They are not in present state, they are not economically viable right now. They require a high initial capital cost and operational expenses hinder the competitiveness of OTC compared to conventional energy sources. Scale and cost. Large-scale infrastructure requirement such as heat exchangers and offshore platforms contribute to the high cost of the OTC. Location constraints. So OTC is most effective in only the tropical regions. So it limits the potential of deployment areas due to ocean temperature gradient, less of ocean temperature gradient. Technological maturity. OTC is still in its early stage, requiring further research and development to improve the efficiency and reliability. Environmental impact. OTC projects may disturb the marine ecosystem, requiring careful mitigation measures to ensure sustainability. Regulatory and policy framework and public perception and acceptance. So to conclude, OTC stands as a promising renewable energy technology, leveraging the vast thermal energy stored in the world's ocean to generate clean, reliable electricity. Mackay Ocean Engineering has been the forefront of OTC development and pioneering innovative solution to overcome technical challenges and drive the commercialization of this technology. So this is the general idea that I shared throughout the presentation, and I think that's the end of it. Thank you so much for listening. If you have any questions, you can ask.
Any questions for Nassim? Nassim, other than this Mackay, did you take a look at other places? Is there any other big one? This is the only one I'm familiar with.
The only one functioning right now. There is one in the Indian Ocean region that they are trying to cooperate with. They are not functioning. They are still in the research stage. They are planning to start operation, I think, around 2024 or 2025. So they're still trying to then they're trying to plan offshore energy plant. So it's tough compared to the onshore plants. So they're taking more time.
The Mackay also does desalination, or do they not?
Yeah.
Okay. All right, thank you.
Thank you.
Now switch to the lecture. So I'm trying to wrap up solar cells so we can switch to batteries. We went a long way. So before I start, we talked about photovoltaic effect, we talked about recombination, and I started talking to you about how do we separate electrons and holes, and that's where p-n junction comes in. Any question from previous lectures that I can address now? And while I'm talking, if you do have a question, just unmute yourself and ask, because I won't be able to see. I mean, if you raise hand or something, I won't be able to see it. I'm on full screen slide, so just jump